But it looks like an ocean, but no salt and no sharks. And so they're quite awesome. Just some other like inland habitats. So this is a wetland from Maine. Oh shoot. We have to reschedule our pontoon trip. So I just remembered, took this picture at the North American Diatom Symposium. Diatoms are a type of algae. And the next meeting is October 2nd. So I just don't go, but that'd be weird. So we'll talk later. So already changing the schedule. And we went to Acadia National Park and we had a permit to sample algae in a lot of the wetlands, which are really nice. Know where that is?
Reelfoot.
Reelfoot, yep. Very unique ecosystem. It's really shallow, it's very strange. Created by an earthquake 200 years ago. Not a lot of lakes like that. You ever been down in here? It's Cane, yeah. You've been to places like it. This is Cane Creek right off the Greenway. And these are two research students I had many years ago.
I have a coworker who works with geology, and they do like fossil collection or like whatever geology does.
Right.
Cane Creek. So he was working there for a couple of years.
Yeah. Oh, you're thinking Coon Creek.
Coon Creek.
Coon Creek.
Coon Creek.
Probably Coon Creek. I don't think there's a lot of fossils in our.
Probably is Coon Creek. It sounds
probably
sensitive.
It does. But Cane Creek's the one that goes through town, and the Greenway is right over there. Anyways, there's just a bunch of different inland habitats. So what's limnology? The scientific study of continental waters. Love that word, scientific. That means collecting data and analyzing it and testing hypotheses and all that good stuff. So I like that word, scientific. And I guess in the syllabus we use the term inland waters, but continental waters is basically any wet place that's got land surrounding it. That's not the ocean.
Study of waters, that's not ocean. Ocean excluded.
Sure, that'll work. We've got a couple of terms that we use to kind of categorize these different habitats. And so if it's a flowing system, like a stream or river, we call it low-tick, and that's how you remember it, low-tick and flowing. See what I did there? And this picture is from the Coweta Hydrologic Laboratory, which is in southwestern North Carolina in the Appalachian Mountains. And Gruba also worked there when he was at University of Georgia. This is the stream, one of the two streams where I did field work for my dissertation, where we were adding nutrients to a stream and then looked to see what happened. And so this pipe here is the sprinkler hose where we were adding nitrogen and phosphorus, and that would dribble into the stream and enrich the whole stream. But you can barely see that stream in there, right? It's pretty small. It's like that deep and that wide, but it flowed all year long, and it's just a really small headwater stream.
I thought that was a pipe.
What's that?
I thought that was a pipe.
Yeah, this pipe that's a pipe there, but the dark area, like the leaves are all kind of hiding it, but the dark area underneath is the actual stream. So yeah, it's kind of weird. Waters that are, quote, still, like lakes and ponds, we call lentic, also wetlands. I've got still in quotation marks because water does flow through lakes, it just takes a really long time. And there's like 26-year-old me in the wetland where I did my master's work doing something. And so we've got lotic and lentic systems, so those are good adjectives to know. We also have the in-between, like a reservoir would be kind of in between, like Kentucky Lake is formed by a dam, so there's a river that feeds it, and so the whole thing is flowing, but it's also a big lake at the same time. So there's also the kind of in between. And limnology, like we said in the syllabus, it incorporates a lot of big fields, and so it's a really just huge area of study, but we're incorporating biology, all the living things that are living in these aquatic systems, ecology, how all those living things are interacting with each other, and the environment, and what's going on in the environment, the chemistry, the geology, and the physics of the chemistry with the nutrient cycling, pH, temperature, all those things. Geology, that plays a big role in what's going on in each of these systems. And then the physics, we'll talk a little bit about the physics of water, which is, here's a secret, I never took physics in college. Woo! But we'll talk about some stuff that is weird about water. It's part chemistry, part physics. Alright, what else? Why should we study limnology? So there's a quote, there are textbooks on limnology, we're not requiring one, but there's one by Walter Dodds and Matt Wiles. And Rubaz, very good friends with Matt Wiles. And they have a quote in the intro part of their book, "Water is unique and has no substitute," which I just think is a great line because it's so true. And Wednesday you'll learn all about the weird things about water. But we depend on water and we can't use something else instead. As I drink my water. It's just water, by the way. So we depend on water, we can't get it from any place else, and we are basically messing with our aquatic resources pretty bad. And so we use water. What do we use water for?
Everything.
Everything, like specifically.
Steve suffered with the electron transfer.
I meant like human society. Yeah.
Oh, drinking.
Power, drinking, cleaning,
Cutting.
Hmm?
Like when you're cutting rocks, you can use the
Oh,
water
okay.
pressure.
Gotcha. Alright. Irrigation. Yeah, so we use water for a lot of stuff. Industry. And surface water would be water that you see like in a lake or a pond or a stream. And this might even be kind of an old number, but we use at least half of that surface water. We pull it in and do stuff with it and then spit out any leftover that we have. So we're using a lot of our surface water. And so that means that we have both a quantity issue, so reducing how much water is in some of these habitats, making less water available to other people, like especially if you're taking water out of a river or a stream, you pull that out and there's less water moving downstream. Georgia and Florida have what we call the water wars, and maybe Alabama is part of that too. Since we've got the big city of Atlanta, which is in the upper areas of a river that flows down to the Gulf of Mexico. And so, who gets the water? In Atlanta, well, this is our water. In Florida, you're taking your water. So, if that makes any sense. So, we have a quantity issue and then a quality issue. So, traditionally or historically, rivers have been a place to dump a lot of crap, literally, literal crap, because it flows away, and so it takes your poop away from you, or takes other stuff away from you, but you're sending it someplace else. But we have a lot of stuff that has either run off the land or we put directly into aquatic systems, and so we're affecting the quality of our aquatic resources. So limnology is helping us understand how all these aquatic systems work and we need water, and so we need limnology. Don't worry about this slide in terms of numbers, but there's one point I want to make here. So this is looking at so this column is the first one, the percent of all water on the planet. And so most of it is in the oceans, 97%. Freshwater lakes, 0.009% of all water on the planet. Rivers, 0.0001% of all the water on the planet. That's a tiny fraction of all the water in the world, yet we are so dependent on rivers and streams and lakes. And groundwater has a little bit more, 0.61%, and we do use groundwater also. So like we have well water here, that's groundwater basically. But these are really small fractions of the total amount of water on the planet. And so the water that we're using and that we're affecting is just, there's really not that much of it out there, which is kind of weird. And then this is just the percentage of water that's in the inland or the continental part. Yeah.
It's weird to think that there's more water in the atmosphere than in the river.
Yeah, good point. Yeah. 10 times, or 10 times? 10, yeah, thank you. 10 times as much in the atmosphere as there is in rivers. That's pretty wild. Okay, so this is the percentage of inland liquid water, so most of it's groundwater, and then, so even of the inland water, there's still a tiny fraction that's lakes and streams. So we have very tiny percentage, but we're kind of messing with it. Residence time has to do with how long any given molecule of water is expected to stay in that ecosystem. So I mentioned lakes do have water moving through it, and the average molecule would stay in an average lake for 75 years. Bigger lakes, deeper lakes would be longer, smaller lakes would be less time. Rivers, a few months. In the soil, we're up to 100 years. Groundwater, 1,000 years. Glaciers and ice caps, that looks related to ice ages. Just a few days with the atmosphere. So different turnover rates of water. So kind of different capacities for like kind of cleansing themselves, essentially. So that's fun. Okay, this graph also a bunch of stuff. It's kind of old and I couldn't find a newer one, but it's from 1950 to 2015, looking at in the U.S. I don't know if it's the U.S. or the world. I got it from the USGS, so it's probably just the U.S., but I'm not positive about that. So withdrawals in billions of gallons per day in public water supply to give to domestic, rural and domestic and animals and livestock, for irrigation, for power, and then other uses. And so it's kind of interesting, we've seen a slow increase from 1950 to about 1980, and then it's sort of, we've gotten a little bit more efficient with water use, so our use in total has kind of gone down a little bit, although individual bars may be a little bit different. So if anyone can find a newer version of that, that would be cool, because I could not find one. But just interesting to think that thermoelectric power uses like the most water. It's pretty wild. So that just fun graphs. Bottled water. ONG. I hate bottled water so much. So from 1999 to 2022, per capita consumption of bottled water has increased in number of gallons. That's not number of bottles, number of gallons. Bottled water is just tap water. Just drink tap water, people, and quit with the bottled water.
Or they should get spring filter.
Yeah, get a filter. I mean, bottled water is maybe filtered tap water, or it might just be tap water from someplace else. So they put it in a plastic bottle that they put in a truck and use a bunch of gas to get the truck to somewhere else, and then you go spend money on this, and it's just dumb. In my day, when we were growing up, we drank tap water and we liked it. We didn't have bottled water. The only bottled water we had was like Perrier, and it was sparkling until Madonna and her stupid Evian water started doing that nonsense in the 80s, and then it just got out of control. So, there's my rant about bottled water. It's just dumb. And I'll be honest, I do occasionally drink it in emergencies, like if I'm somewhere and I'm dying and that's all they have is bottled water, I'll have some. But I got this out of our water fountain in Brim Hall, and it's just lovely. And I try to drink like at least 2 quarts of water a day. It's usually more. So it's okay. All right. This is a wild graph here showing around the world top importers and exporters of various things, but top 10 freshwater consumers and kind of where that water ends up being used. And so China and India and the US are in the top, which makes sense. China and India have the highest populations, and then the US is just kind of notorious for, with our population size, we just use a lot per person. And just showing that household use is not huge, industry is not even huge, but agriculture is really big, and then this looks like other agriculture as well. So there's a lot there. Do I have this going anywhere? So all these humans, we've got to feed them. And now we're showing. So I like this population clock just to remind us that as this world population keeps on ticking up and up and up and up, we're gonna need water for all those people and all of the things that support all of those people. So our demand for water is only increasing unless we can get more efficient. But this only just keeps going up.
I was watching Paula's granddaughter on the other street.
Oh yeah?
Yeah, see,
Oh, okay.
they're right there.
Hey girl. But back when I was in high school, I remember when we hit 4 billion. Pretty exponential.
I wonder if there's a Earth decline, like there's a Earth crash. Thank you guys.
Yeah, but we're still increasing.
Yeah, there's
Yeah.
been no net change in the exponential growth rate,
Yeah.
despite all these things, no war, no nothing. It's every effectively exponential growth rate except plague.
Yeah, so even if the rate goes down, as long as it's above 0, we're still gonna increase. That.
I want to see what because they said like death every 11 seconds.
Mhm.
I want to see what the death counter would have been in like if we were in a war, like if it was wartime.
Makes me think about it.
Not a good thing, but
Right.
it's interesting to see.
Okay, this is a little bit of an older article about drought in California, and so I just wanted to kind of show how we have these. We know we have dry years and wet years, and we have these different cycles, and we're having a very dry August this year, which hasn't happened for a while. But this is from California. They looked at tree rings and looked at growth rate, and then for rainfall from how much the trees have grown. But what this shows is a tree from 800 AD to about the year 2000, and the red is showing years that it was drier, and then the blue wetter than average. And so for 700 years, it was mostly drier than this average, and then since human civilization has really taken off, it was wetter in California, and with little dry blips, and now we're seeing more droughts and wildfires and that kind of thing out west. And I remember one of the geography classes I took, my professor was talking about this kind of thing, and he's like, it's basically been a nice day in California for the last 50 years. So that would be since the 30s. And so they've had plenty of rain to grow all these crops, and we get a lot of our produce from California. But like if you look at the long-term situation, we could have, you know, much drier weather for a really long time. And that's just kind of how that works. And so I'm gonna try to, this is just kind of cool. Yay. This drought monitor map. And so it just shows you, and I think you can go back in time too and look at it, where droughts are. So the redder it is, the drier it is. The S means there's some short-term drought. The L means there's also long-term drought. And so we're getting into the drier there, but we've had a few wet years, so it's taking a bit. But it's interesting to watch that. And California's doing okay right now. In years past, they were not doing very well. But some places are dry and some places are not. So it's a lot of variability. And I guess we can closer. Maybe we can look at counties. That's relatively good. So Weekly County says none, which surprises me. Huh. That can't last. Next week we'll be yellow, I swear. And then thinking about drought out west, so this is Lake Mead, where the Hoover Dam holds back the Colorado River and makes Lake Mead. And there's a picture, same spot, 1983 versus 2007. And so just reduced rainfall and perhaps human consumption a little bit brought the level of the lake down a lot. a lot. A different view comparing 2015 to 2017, so things were actually improving here. They talk about the bathtub ring, where it had been underwater for a long time, so it's kind of bleached out. And so you can see that kind of shrunk between 2015 and 2017, but that was really low. I don't know if you remember a year or two ago, I forget when, it all runs together after a while, but in the news, it was a different lake, I think, but the water was getting low enough where they were starting to find like dead bodies in barrels and stuff like that. Like mob dudes from Vegas had dumped out in whatever lake it was, and so so drought can be an issue. And people should not live where there isn't water. So quit moving to the desert, you idiots. Another rant. Oh, and there's a fun little graph. Lake Mead monthly elevation at Hoover Dam. So been declining up to probably 2022. I don't know where we are now. I will look one day, unless I forget, which I probably will before I leave today. Alright, how are we doing here? Good. And then, so that was a lot of like quantity issue. This is a quality issue. So here's Florida, central South Florida. And so water basically flows down the state, and rivers kind of end up just flowing down through here, through the Everglades and into the ocean. And so there's a lot of like sugarcane plantations and residential stuff, and so a lot of nutrients have been flowing into the Everglades and then out into the ocean, and also lots of coastal areas are getting a lot of rivers that flow to the coast. They're releasing a lot of nutrients as well, and then you get things like algal blooms, and I love algae, but there's these algal blooms where there's so much stuff, it's gross, and it's not good algae. It's like, could be toxic algae. Not all algae is toxic, but there is some that is. And if the blooms are really bad, they can even like put toxins into the air and cause respiratory issues. And you can't go swimming, you can't do any recreation. If it's fresh water, you can also get algal blooms that are toxic, and then you can't use that water. Like in Lake Erie, they get toxic algal blooms, and so in Toledo, you may not be able to use the water for anything. Like they don't want you to take a shower in it. You can get skin rashes and stuff like that. So, anywho, so nutrients are an issue, so quality is an issue, and I'll talk more about algal blooms later on. And I guess I have a little link to red tide. Heard of red tide? Red tide looks kind of red, and it's a type of algae called the dinoflagellate that we'll talk about in the algae lecture. It's a little bit reddish here, but the pigments are kind of a brick red. And this toxic algal bloom, they make toxins that, again, can aerate and cause respiratory issues. If there's shellfish living in those areas, like oysters, they're filter feeders, so they filter water and they're eating all this algae that's blooming. And then they can absorb toxins, so if people eat oysters that have been in a red tide, they can get like paralytic shellfish poisoning, which can paralyze all your muscles except your diaphragm for a while, and you have to get on a ventilator and try not to die. And then there's diuretic shellfish poisoning, which diarrhea, you know where I'm going with that, so unpleasant. Yeah, and it's generally not good, no bueno. And yeah, but I'll talk more about algal blooms. So we have toxic or harmful algal blooms in the ocean and in fresh water as well, in inland water. So for all of these reasons, we need to understand our aquatic ecosystems. That's why we're here, so that we know more. Questions?
Does the red tide affect the shellfish because they take it in, or is it
Yeah,
just?
it can eventually kill them. I think it takes a little bit, but I think it can kill them. I don't know if you've ever heard, only eat shellfish in months that end in R. And I think that's one of the reasons. We've always had some toxic algal blooms, but now they're just becoming more and more common. The more and more nutrients that we dump into aquatic places.